So this talk will be more about like what happens when the data that you stream from Kafka lands into a data lake and then gets used for analytics and machine learning. So 3 years ago, LinkedIn started a journey moving its data lake to a new table format, Apache Iceberg, new back then, Apache Iceberg, and turning our existing data lake ecosystem into a data lake house, if you will. That's the current terminology around it. One of the challenges that we had realized is we didn't have a good story around managing data in data lakes, and also like bringing Iceberg meant that we had to really step up on how we would manage these tables in data lake houses. So with that that problem statement in mind, we created OpenHouse, a control plane for managing tables in your data lakehouse deployments. So management is a spectrum. Like you could think about management can include like governance, optimizations, stuff like that. So today in this talk, I would like to go through our journey and what are the developments that are being considered in the current OpenHouse releases, and then yeah, let's get started. The QR code there is for the GitHub repo. Like OpenHouse is open source recently, so if you are interested in playing with that, you can go to GitHub LinkedIn OpenHouse. Quickly about me, I have been at LinkedIn for about 3 years. I started OpenHouse. I've been an architect of it and also scaling Apache Iceberg to LinkedIn's exabyte scale. Before that, I was at Lyft in the autonomous vehicle division where we were trying to build self-driving cars, and I was leading data. And before that, at Chintry and VMware, working on transactional storage systems and log structured file systems. So the agenda for this talk will be, we'll start about talking about this thing about big data management, right? So there has always been this inherent tension between how much control data infra teams want on their offerings and the flexibility the end users desire when you talk about big data, and specifically talking about open source data lakes, not data warehouses. So that's where, like, if you put this into perspective, what LinkedIn ended up having is a very siloed data lake architecture. We'll go through that. Then we'll introduce OpenHouse and dive deep into what OpenHouse is, and finally conclude with the future work. So like I was saying, like in the big data ecosystem, right, there's been this tussle between control and flexibility. So on one hand, you have your cloud data warehouse solutions that allow you to maintain tight control over the system, which allows data infrastructure teams to ensure proper governance, security, performance. However, these systems often lack from flexibility and scale. So that's where like open source data lakehouse systems come into play. The key distinction in these two categories stem from what are the constraints they impose on their offerings. So for example, cloud data warehouse solutions will expose a narrow API, often SQL, on top of a managed table offering, right? Whereas open source data lakehouse deployments expose a much broader API. It could be a data frame API, it could be SQL directly on top of unmanaged tables or unmanaged data. So the question that we had at LinkedIn, which we always have had a self-managed open source data lakehouse deployment, and most recently Apache Iceberg based deployment, like how do we provide a managed experience to our end users? And here end users are data scientists, data engineers, ML engineers. And as a part of the data infra team, like we want to provide that managed experience so that they don't have to dilute their core product focus, which is not infrastructure. They're there to solve their business problems. So essentially that was one angle of it. And then the other angle of it was we as a data infra team were left with little control over our data lake because we didn't really have stronger contracts. So that's where LinkedIn was. So this is where we ended up with. We had a siloed data lake architecture. So on the top left, you see the LinkedIn application generating tracking events, passing through Kafka, and via a managed ingestion pipeline, they would land into our tracking data lake, if you will, which was comprised of HDFS and Hive Metastore. Further, at LinkedIn, we are also organized as like lines of businesses. So you have your ads, premium, jobs. Essentially, each line of business will generate petabytes of data, and then they would manage that, self-manage that in their own private data lakes. And finally, if there is a need to share data between these lines of businesses, there is another managed ingestion pipeline that would copy that data from their private data lakes into a centralized data repository. So as you can imagine, often these LOBs needed to share data with each other. And the process was to first copy that data into a centralized data repository. This centralized data repository had features like auditing and security access control built in a way that we made sure that the sharing cross LOB was compliant. Only through this cross LOB data sharing was possible. But the whole fact that you have to copy data to share is not scalable. Onboarding and maintaining these kind of scheduled copy jobs came at a high toil for data infra teams and also resulted in poor user experience. Moving on to decentralized data management. So I talked about private data lakes. Every LOB has data. Who's managing that data? So what ended up happening was that the responsibility of managing with that data was with the LOBs themselves. And as I pointed out, that's not their primary job. Their job is to like drive business objectives. So that diluted their core product focus. And finally, if you think about it, data lakes, the kind of contract they expose, that you can access data as files on a blob store or as through tables, that kind of a loose contract kind of makes it really difficult to build tools on top of this data. So for example, like centralized tooling for auditing, compliance, discovery, data quality, like had to support these diverse set of data scenarios. So essentially building these data tooling became more complex. So if you put all these three things into perspective, right, the expectation that end users have is they interface with a managed data infra offering, while in reality they deal with self-managed high-toil data infrastructure. While data infra teams, what they want to expose a narrow API that they can govern and optimize centrally, while in reality it's best effort and end users are playing a big part in that. So we wanted to address that. So these three user stories emerged around data sharing, data management, and data tooling. As a user, I want to share data without incurring that data copy. As a user, I want to delegate data management activities which are super critical to data lakes to a centralized platform. And finally, as a data platform tool developer, I want to interface with a narrow API and an opinionated data lake. To address these user stories effectively, we took a comprehensive approach in the way we conceptualized a managed data lakehouse offering called OpenHouse, leveraging Apache Iceberg as a table format and HDFS as the underlying technology for data persistence. LinkedIn's infrastructure is on-prem, so HDFS is what we use. So the outcome was we were able to remove the data silos and provide consistent governance standards and centralized data management practices through these three key strategies. So the centralized data governance allows us to provide granular data sharing without having to do those additional copies, and we'll see in the future slides on how we do that. Declarative data management is essentially what we say is like the end user sets a policy and then forgets about it, right? The system should reconcile the observed state with a desired state that the user wants. And finally, creating this opinionated data lake, a bit more of an implementation detail, but an important one, because like exposing tables as the only data access interface is a change in the behavior for many of the data lakehouse users, and on top of a protected storage namespace. Turns out it's a hard thing to do. We have made some progress around it, but I don't think we are fully there. And there is a slide which will talk about it. So back to this control flexibility tussle. So once we have this managed lakehouse strategy with OpenHouse, we fall somewhere in the middle of the spectrum, where we expose a narrowish API to our end users on managed Iceberg tables within LinkedIn. Now, control that liberates is that paradoxical idea, is where a well-implemented control mechanism can actually empower data infra teams to govern and optimize their data infrastructure better, and also end users they don't have to worry about low-level infra concerns. OpenHouse essentially is a materialization of this paradox. So what is OpenHouse? The product itself is a control plane for tables that comprises of a declarative catalog where users can seamlessly define tables, their schemas, and associated metadata. And in addition to that, the OpenHouse control plane also includes a suite of data services essential to reconcile the observed state of the table with the desired user-defined state or system-defined state. Before we jump into the different building blocks of OpenHouse, I want to quickly highlight that OpenHouse control plane is architected in such a way that it should seamlessly integrate with the rest of your data lakehouse ecosystem. So for example, the typical building blocks are compute engines like Spark, Trino, Flink, and then you have your table formats like Iceberg, Delta, Hoodie, and then storage is could be HDFS on-prem, or it could be any blob store like S3, Azure Blob Store. So it seamlessly integrates into your infrastructure. Now we'll start diving into each of the building blocks of the control plane. The declarative catalog to start with. So the declarative catalog part of the OpenHouse control plane is essentially replacing Hive Metastore at LinkedIn. It exposes 4 different kinds of APIs: core API, sharing, governance, and policy management APIs. If you think about core APIs are on par with what Iceberg's REST catalog provides. So essentially, these core APIs allow you to perform the standard DDLs and DML statements from Spark and Trino, as shown here. In addition to the core APIs, OpenHouse also has sharing APIs. Now, many of you might have used data warehouses, which allow you to execute grant revoke SQL statement to share data, and then data is in like tables are instantly shared. We wanted to bring the similar kind of user experience to OpenHouse and allow sharing, democratize sharing, and instant sharing without any data copies. So we made SQL changes to Spark to allow this kind of capabilities. So the first is a statement that the users execute. As an owner of my table, I am setting sharing equal to true for this table. Now, once I have set this sharing equal to true, then I can say I can grant read privileges for this table to any other user. So grant select on the table, which is the last SQL there, allows you to share a table with someone else. Then there are more sophisticated sharing or responsibility sharing kind of capabilities that we expose. Like for example, manage grants on a database would allow you to give another user permission to grant permission to someone else. Similarly, grant create table on a database will allow you to grant that user permission to create tables within a database. So that's the sharing APIs. And we'll start with talking about the APIs, and we'll talk about how they are implemented in the next section. Then you have the governance APIs. Again, we've been talking a lot about shift left in context of streaming, but shift left also applies to lakehouses, where you have your users having a full flow, right? They are creating a table, they are altering some metadata for the table, they are inserting data into the table, right? So at that point, you have the user's attention. So you want to capture as much as metadata, if you will, from the user as much possible. And for that, you have to really make it simple for them to set that metadata. So this is essentially another one which we have extended the Spark SQL for our end users to essentially say alter table, modify column, email is set tag, PII or HC. Now you can take it one level further, because sharing is what we started talking about. What you could do is you could do granular sharing on column level. Now what you could do there is with the second statement, now if your table has a column that is being tagged as PII, then you can say grant select PII on the table to a user. And only then that user can read that column. So essentially that allows you to do granular column level sharing. And if any user doesn't have this kind of a privilege, if they do a select star from a table, the query will fail with a permission error. So that's the governance APIs OpenHouse expose. And finally, the policy management APIs, which essentially are in two use cases that we support, like one is retention and one is replication. So retention essentially is like you want to expire data older than a certain time. So like you have a TTL on your data. So users can just go ahead and set policy retention equal to 30 days, and data will start like getting expired by a by a background job. Then you have replication. Now you want to replicate the table from one data center to another data center. Instead of like making a lot of knobs changes here and there, it's as simple as setting policy replicate to different data centers. So that's the user experience part of OpenHouse, where end users use SQL as a primary way to like declaratively set what they want that particular table state to be. Moving on to the suite of data services. So we talked about like the policy APIs and the sharing APIs, but somebody needs to make it happen. And that's the job of the suite of data services. So data services are 4 categories. You have retention, replication, you have iceberg maintenance, and data layout optimization. So the first two that we talked about in the policy APIs, like setting retention and replication, are taken care by the retention data service. And replication is the next one. So we'll talk about each one of them in more details in the next few slides. So when you talk about data retention, like let's say you have a table that you're appending to every day. Now you want data older than a certain date to be expired. Like how do you like think about TTL on any column? So what we said was we'll support TTL on a time partition tables. So essentially what that means is you have a table, one of the column has timestamp values, and then you have partitioned that table based on that column, and you're setting a retention on that. Why that constraint? Because deletes in data lakes or data lake houses in Iceberg can be expensive. So you want to make it a metadata only operation. So that's one part why we do partition expiration. Now, coming from a Hive world, if you think about it, your data, your timestamp can be in a column which has a type string. Now you don't know how the values in that column are formatted, like what is the date time format that was used when the data was inserted into that table. So that brings more complexity into the implementation of the retention. And sometimes like we have to ask user to specify more things. Like the first example is pretty straightforward, right? You have that column. The column is of timestamp type, which Iceberg provides. Now you essentially know that at the time of writing, Iceberg has verified that whatever data will be written to that column will be a timestamp value. So you have that constraint that you already have it in place. So it's easier for you to like not ask for any additional pattern. But when the same column is of string type, but it is holding some kind of a timestamp value, right? Like just YYYMMDD, then you don't know if it is like in this format or is it just YYY, is it YY with hour? So at that point, like you need to ask your users that, okay, provide us the pattern. And users provide us the pattern, and sometimes still like bad data can come in to that column, and then you have to deal with it from an operational standpoint. So retention sounds like very easy on the paper, but when you start thinking about these edge cases, things start getting gnarly pretty soon. Replication is the other feature that OpenHouse provides. It essentially allows you to incrementally copy data from one data center to another. And this is important because now with Iceberg, we have that capability of computing diffs very efficiently. So essentially what we are doing is incrementally computing that diff, replicating it, and then like moving on to the next diff. So if you see in this, like the triangles represent snapshots, which is like the concept of a version in Iceberg. And one of the advantage of doing this snapshot level replication is essentially now if I run a query on the source cluster, and if I run the same query on the destination cluster with the same snapshot being pinned, I get perfect query reproducibility, because the data is exactly the same. Essentially, think about it as you have a database and every transaction of that database is getting replicated. So this is very powerful when you have machine learning data set, like training data sets being replicated, and you want to make sure that you have that kind of a reproducibility when you run the training job. There are complexities in Iceberg when you have to deal with something like full paths in metadata. So for those who have used Iceberg, they will know here that if Iceberg metadata will encode the full path, and the path may not look the same on the destination. So then you have to make a trade-off, like if you want to go with that, or do you want to like rewrite the metadata on the destination. I think there are options there. For us, we were able to use catalog as a way to decouple this essentially the path into two categories. One is essentially the cluster prefix of the path, and then the rest of the relative path that gets stored in the Iceberg metadata. And that's how we were able to work around this issue with the file paths. Moving on to Iceberg maintenance. How many of you have used Iceberg or like productionized Iceberg? So, a couple, yeah. So I think this is one of the most important part when you want to productionize Iceberg. Now, like in the morning, we heard that there is a table flow that takes your data from Kafka into Iceberg table, right? But once that data gets into Iceberg table, you still need to think about how you're going to expire older snapshots in Iceberg, how you're going to delete orphan files, right? How, if there was, say, a create table as select transaction or any Iceberg transaction that kind of aborted, then you are left with orphan directories. So essentially, the reason why this is important is Iceberg is supporting versioning, right? And there are two reasons why this is important. One is essentially you can keep writing to an Iceberg table and newer versions will be generated, right? And you will fill your space, or your storage will grow infinitely big, right? So the cost is one reason. The other reason is compliance as well, right? Let's say you are doing deletes of the data because your compliance requires you to do that. Then at that point, hard deleting the data is also important. So essentially, orphan file deletion should run on a schedule, monitored, so that the table remains in a compliant state all the time. And finally, as we onboard CDC traffic on Iceberg, there is a lot of updates coming into Iceberg, and then and those get captured as metadata files in Iceberg, which is you can trade off write throughput for read performance. Essentially, that's the trade-off you have. So if you go for a very high write throughput scenario, then you kind of have to do some kind of a compaction of those updates or the deletes on the Iceberg side to make sure that your read performance is high. And we'll talk a little bit about that when we talk about data layout optimization in the next few slides. So this is something that we have been looking at. This is pretty recent. We are starting to scale to a point where, again, we don't want to push the complexity of how optimal the data layout should be to our writers, writers of the Iceberg tables, right? We want to let them write it, and then we want to make a decision if a certain transaction that got written into a table should be rewritten in a way that will be more optimal. So essentially, the problem statement is now we have about 15,000 tables in our in OpenHouse at LinkedIn. Eventually, we'll have about 100,000, 200,000 tables. Data layout optimization is essentially you write the data, and then there is some background job that is rewriting that data to be in a more optimal format. Now, at the scale of 100,000 tables, we can't expect that we'll sweep all the tables and make sure we'll rewrite all the tables. That becomes prohibitively expensive from a CapEx and an OpEx standpoint. So what we started thinking about is how do you select the top K tables for data layout optimization out of all these 100,000 tables? What is the best optimization strategy for a table? And what is the impact of that, right? So then if you think about this problem, it's essentially a multi-objective optimization problem. There are multiple objectives that you are evaluating at the same time, and different organizations might have different importance given to different objectives, right? One could be reducing small files, right? Number of objects in your buckets will grow if you have too many small files. So doing some compaction there, that may be important. Or just the size of your files might be, you want to compress those files better. That might be important to your organization. Or you may be saying that, okay, no, this table is very sensitive to query performance, and hence I want to reduce the amount of work I want to do during a query. And finally, all this while also, like, when you are running against a very tight budget of how much compaction budget you have, like in terms of compute capacity, in terms of operational bandwidth, how much of that you have. So all these trade-offs are pulling against each other, and hence we have to optimize them together. So we are taking that approach, and we are saying that, okay, every objective has a weight that can be tuned depending upon what is important to a certain organization, and then we kind of create a bias towards that objective. Once that's done, you turn that multi-objective optimization function into a single objective which can be easily sorted and ranked, and then you pick the top K based on a certain threshold that you have around CapEx and OpEx budget. So this essentially allows you to do more automated data layout optimization at a scale of 100,000 plus tables. I'm sure this will start getting more and more interesting when we add query performance. Like right now, our primary focus is reducing small files, but as we venture into improving query performance on iceberg tables, that will be a very interesting angle. At that point, I think every organization, different scale organization, could benefit from something like this. Moving on to security. So we said we support sharing. So one of the things that we had to rethink is, how do you make sure all the data, how do you bring ACLs, how do you set up ACLs in such a way that you can do instant data sharing in lakehouse architecture? Think about it, you have a bucket, you have multiple tables in that bucket, and then what is the right policies that you want to, IAM policies that you want to attach to every prefix in that bucket, and so on and so forth. So essentially that's the problem, and that kind of ties into the whole opinionated data lake architecture, where we say that we have a protected namespace, we allow a certain set of permissions being set. So from a security standpoint, we have token-based authentication that Catalog supports. In terms of authorization, we have role-based access control for table metadata operations that kind of gets translated from grant revoke. In addition to that, for data ACLs, we kind of delegated to the storage, although that kind of has scalability limits, which we'll talk about in the future work slide. And finally, we have a kind of a system user for all the data services that we run for periodic maintenance. The observability part is key, because the better the observability we have, the better we can innovate, right? So we log a lot of user actions that are happening on the table. We log query projections and predicates so that we can say that, okay, this column looks like a good candidate for clustering, or this column looks like a good candidate for sorting. That kind of optimizations you can start doing. Similarly, for transaction reports, essentially you can say that, okay, now a commit happened to a table, right? I'm going to trigger a replication right after, because I know that there is a trigger commit, there is a new write transaction that has happened. Or I'm going to look at the data that was written as part of the transaction and see if I should make a layout optimization decision for that particular transaction. And finally, we are saying that we have this suite of data services, but if they are not working in a healthy manner, they are of no use. So essentially monitoring them is super critical for a fully operational lakehouse. So architecture for this looks something like this here. So you have the compute engine, user interface with the compute engine like a Spark or Trino. And then you have, as I said, it seamlessly integrates into the catalog layer for these engines. all these engines have a very standard catalog APIs, so we implement those. And Iceberg, we also integrate with Iceberg data source APIs. So essentially that allows us to have a very thin client from OpenHouse catalog standpoint within the engines. And also the other key part is this is interoperable. So you don't need to keep implementing that every time there is a new engine. And the other part is suite of data services essentially uses compute engines and the catalog service to make sure they can run the maintenance jobs. Talking a little bit about opinionated data lake. It turns out it's a hard problem because you don't have a server that you can throw a SQL at it and then you get the response, right? You have a bucket which has files, and then you have some kind of a table abstraction on top of that. So how do you really put constraint that table is the only way you can access data? So there are things you could do, but I don't think we have gotten all the way. Also, I don't know if we will be ever able to get it. There may be reverse engineering happening to get to files and then access files directly. But this is one of the design patterns that we have in OpenHouse. So what we have done is we have put constraints that anything in this protected storage namespace is Iceberg. Table directory path is obfuscated. In Hive, you could just go and have a table name. But when you create a table in OpenHouse, we create it in a location which you have to reverse engineer to find out where it is. We have disabled directory listings. So essentially, if in Hive you are doing a lot of directory listing to get files and putting it into a data frame, then doing data processing, we have disabled that. So there's no way to the Hive style data processing doesn't work in this space, well, at least in OpenHouse. And then no support for external tables and storage permissioning spec also, like I mentioned, it's very opinionated. Nobody can just go and change those permissions within this protected bucket, if you will. Quickly, current state is we have 13,000 production tables internally within LinkedIn, 750 daily active users, 50,000 jobs that we run every day. We have recently open sourced it, full Spark engine support with the extensions, the Spark SQL extension that I was talking about. Then Trino, DDL, DML is working internally. We soon to be open sourced. And table formats right now supports Iceberg. So top of mind is the layout optimization essentially right now. Iceberg adopting that table format has some write amplifications because you have multiple versions and metadata growth on the storage. So essentially you need to start looking at those things. Then, like I was saying, you don't want to push the complexity of what is the right way to write data into the storage to the end users, right? You want to you cannot control things, right? They will write it their own way. And if you have thousands of users, who are you going to chase? So essentially dealing with that untuned Spark writers is another one. Finally, storage security policies, limits, IAM also has a lot of limits. When you set policies to a bucket or a prefix, then at that time, we are moving towards a more token-based ODZ model where catalog will mint tokens and then engines can directly access data. And finally, out-of-band mutations Iceberg metadata is stored on storage, and we have had times where somebody came and deleted some metadata files, and now we have dangling references. So that's a corrupt Iceberg table. So how do we prevent that from happening? This kind of goes into that whole opinionated data lake paradigm. With that, thank you. This is OpenHouse, instant secure sharing, centralized data management, and stronger contracts.